Let's continue with related rate. Again, a related rate, the change of rate of one quantity affects the change of rate of a related quantity. And this will be, I believe, example number 3 in this group. And in this case, we have, let me first give you the overall outlay of the problem, and then I'll write it down. Imagine that you have a water tank that is shaped as an inverted cone, a cone where the vertex is at the bottom and the white base is on top. So this is the container, and we pump water into it, and the water is pumped at a certain rate. And let's say in this case it will be 2 cubic meters per minute. We need to find the rate at which the water level is rising. Okay? So imagine you pump water into a container, the water level is rising. Now, it's pretty straightforward if you have, for instance, a cubic container. But even in this case, you need to calculate the rate at which the water is rising. In this case, we have an odd shape. It's an inverted cone. So let's write. Okay? A water tank has the shape of an inverted circular cone. All right, and with base radius equals 2 meters and height equals 4 meters. Okay? All right, here we go. If water is being pumped into the tank, at a rate of 2 cubic meters per minute, find the rate at which the water level is rising. When the water is 3 meters deep. Okay, a typical worded, long, lengthy worded problem. This is if there is something in common to this related rate business. You have long description of the problem, and then you need to figure out what's going on. And to figure out what's going on, you always want to start with a little sketch. And here you can use a little bit of imagination. And this is the tank, so to speak. And here's the axis of the tank. And I'll place my coordinate system at the bottom. If you look at your book, you'll see that I'm doing it differently. I'm placing the coordinate system at the bottom. I think the book will place it on the top. Now imagine something like this, that there is a kind of a water spigot or something like that. right, coming off, let's say, imaginary wall, and you have here a water tap or valve. So the water is coming out. As I said, you can use a little bit of creativity here to describe this. So the physical dimension of this container or this tank is the height. So let's call it h equals 4 meter. And also the radius of the base, which is right there, it's r equals 2 meter. Okay? So the diameter and the height are the same. So what happened is, as we pump water, then the water level is rising. At one point, the water level is right here, and right here means the water level is 3 meters. So we are looking at y equal 3 meter, and this is the water, so let's shade it a little bit like so. Okay, so the shaded area is, the shaded volume is the part of the volume that is already filled with water. What happened is there is a rate of change going in this direction, and therefore we call it dy dt. And this is the rate at which the water is rising. Okay, dy dt. So y, when y equals exactly 3 meter, then we have a certain rate. And notice that at the beginning, since if the change in volume is constant, if we keep pumping at a rate of 2 cubic meter per minute, when the cross-section of the container of the tank is small, then the water will rise quickly. But as the cross-section area of the tank, the circular cone, is become larger, then the water level is rising slower and slower. Okay? So, time to write what we know. So this will be our given. So what is given to us? The physical dimension. Okay? So we know that as far as the tank is concerned, we have r equals 2 meter and h equals 4 meter. Also, we know that the pumping rate, we call it dV dt, is 2 cubic meter per minute. And this is, we are in particular interested when y equals 3 meters. So we have 2 cubic meter per minute. Okay. This may be a constant. In other words, maybe the pumping rate probably is the same regardless what is the height, but we are interested in particular when the height equals 3 meters. That's why I put it this way. All right, what we really need to find is dy dt. So, how are we going to find this quantity? Well, we need to look at the volume, or the volume that is represented as shaded compared to the overall volume. Okay, so we have two volumes. We have the volume of the tank, that's fixed. And what is the volume of a cone? If you recall, I addressed that earlier in the semester. If you consider this to be a cylinder, in other words, at the bottom instead of the vertex, we have another circle equal in size to the circle on top, then the volume will be the base multiplied by the height. Since we have a cone, then that will be 1/3 of it. It's the same with a pyramid, and something that, as I said, I mentioned earlier. So it will be, the volume will be 1/3 of the volume of an imaginary cylinder, circular cylinder. And the circular cylinder will be the area which is pi r squared times the height. So it's 1/3 pi r squared times the height. Okay? Now, what about the volume of the water already in the tank? Well, that's another circular cone, except it's smaller, right? So that will be in terms of r and y, where r is the radius of this circle right there on the top. Okay, so you have r is this radius, big R, uppercase R is the fixed radius, the radius of the container. But as the water is rising, lowercase r, the radius of the circle, which is the water surface, is also increasing. So it will be 1/3 of this area shaded twice, the surface area of the water. So this will be pi r squared, r lowercase, and the height will be y. Okay, so we have these two quantities. The thing is this. We know that dV dt is 2 cubic meters. So we know how to take the derivative with respect to the volume of the water. That's given to us. But we have two variables, y and r. We need to express one variable in terms of the other. Turn out that we can do so. And the way to do it is using similar triangle. And this is something that you'll see quite often when it comes to related rate. On several of your homework problems, you have to use this approach. Okay, can I remove this page? You all caught up with me? All right, so for on page 2, we're going to try to find out a relation between the two unknown y and r. And to do so, we look at right at the similar triangle. Let's look at the a profile, another cross section of this sketch, but let's go from the axis of symmetry to the right side. Okay, and we'll flatten it into a two-dimensional image. So here's the axis of symmetry right there, with the top is right here. So we have this triangle. This triangle represents the tank. So the dimension will be, this base will be r, and the height, of course, will be h. And again, we know that this is 4 and this is 2 meters. Okay. Now the water will be represented by the shaded triangle right there, where this quantity right here is y, the water level, and this quantity right here is r, the radius of the surface of the water. Okay, and now we can see that y, the ratio y to h, is the ratio r to r. Okay, by similar triangles, we say that y over h equals little r over big R. And this will allow us to replace r in terms of y. We can write r, well, let's write it in, let's put numbers here, y over 4, since big H is 4, equals r over 2. And now we can write that r by itself will be 1/2 y, 2 over 4, by just by cross multiplication and so on, or just solving this proportion equation between two ratios. Okay, so now we're going to write that the volume of the water, because we can substitute r with 1/2 y, will be 1/3. Instead of pi r squared, we'll have pi y over 2 squared times y. Okay, so let's simplify it, and we have 3 times 4, so we have pi over 12, and then we have y squared times y, pi over 12 y cubed. Now, we're going to take this equation, v equals pi over 12y cubed, and we take the derivative with respect to the time. Okay, so we're going to differentiate with respect to t. Okay, so on the left side we have dv dt. Well, we know what's dv dt. It's given to us. And here we have pi over 12. The derivative of y cubed with respect to y would be 3y squared. And then the derivative of y with respect to the time will be dy dt. Okay? And if you work on it a little bit, you simplify it, and you get pi over 4 y squared dy dt. Okay. Spike, your question.
Why did you substitute in 3 for y?
Y is 3 at a certain point in time. But I need to find a general expression for all the time. So this is a case where you express one variable in terms of the other, not one particular value in terms of the other. So it's a good question. Why I cannot substitute y with 3. I'll do it eventually, but not when I express one variable in terms of the other. Now here we have, actually this is the time to do it, because what we want to find is dy dt. Now notice that every other quantity is given to us. Right? dv dt is 2. And then we have pi over 4, which we know. Y squared is 3 squared. So here we go. Now, and dy dt. And now we are good to solve it. And, of course, this will be 8 over 9 pi, I think. Okay? So dy dt will be 8 over 9 pi. And the unit will be meter per minute.